Hello, welcome to episode 2 of the Think Distributed podcast, where we're going to talk about causality today. So we have some really awesome thought leaders on the panel today, so why don't we just go around and introduce everybody, starting with you, Carlos.
Hi, I'm Carlos Baqueiro. I'm an assistant professor at the Universidade do Minho, which is in Portugal, and I like to do research on causality and CRDTs and other stuff.
Marek.
Hi there, my name is Marek Zawierski. I'm a grad student at UPMC Lipsis in Paris, in INRIA. I do research in distributed systems, especially weakly constant systems. So I use stuff like vector clock dispersion vectors daily. I hope we're going to talk about this stuff today.
Peter.
I'm Peter Aylis. I'm a grad student at UC Berkeley. I study distributed systems, mostly distributed databases. I like stuff that goes fast, is always on, and is useful.
Cool.
Hopefully all three.
And I'm Chris Micklejohn, software engineer at Basho Technologies. Cool. So, Peter, why don't you start us off here with the example kind of application we're going to kind of talk through to help understand causality today.
Sure. So we basically were thinking of examples that would be useful to start off with, and we realized that basically everyone has probably interacted with a document editor. And increasingly, we're seeing document editors that basically are in the cloud or essentially allow multiple people to make updates to documents and share those edits. Now, when you're actually making an update, you may not be, say, connected to the central server, or even if you are, the central server might have multiple copies of the data that are located, especially increasingly for services like Google, in different parts of the world. And this provides both fault tolerance, it also provides availability, and it's generally useful for performance. So if I'm on, say, an airplane, it's nice if I can have a copy close to me, and then when I get off the airplane, suddenly all of our document versions should magically agree. So the problem in this case is when we perform concurrent updates, such that when we're performing an update, we only have, say, a partial view of the system state. That is, there are multiple copies of the data. Not everyone can see all copies at all times, or it would be prohibitively expensive to otherwise do so. We need some way to track essentially what happened before each update and what causally influenced each update. That is to say, if Marek and I simultaneously at the exact same time update the document, he in Paris and I in the United States, we should somehow detect that Marek and I essentially made concurrent updates to the document. So the challenge in causality, which applies to many problems in distributed computing, is to first identify, or is mainly to identify when events were unrelated to one another. So Carlos,
Okay.
Carlos will basically explain in more theoretical terms what this actually means, or characterize causality.
Okay, so this concept was introduced to distributed systems by Lamport in '78, and it built on the causality concept like from physics. So it means that you cannot be influenced by something that you haven't seen yet. So if the sun suddenly disappears right now, we are not. It already happened, but we are not influenced by it. It takes some time for this information to get to us. So it takes more time for things that occurred far away from you to influence you than it takes for the things that like you are doing yourself. So bringing this to the document editing. So I'm editing the document and I'm disconnected, and so the edits that I'm doing, I observe them immediately, and they influence me immediately. But the edits that Marek is doing in Paris, supposing that he's disconnected at the moment, I'm not seeing them. So later on, when connectivity is again possible, or it took its time to propagate, I want to detect that the Marek did a concurrent edit with what I was doing. Because otherwise the problem is very simple. So suppose that he didn't do any concurrent editing, he just had his local copy of the document, and it was by chance only me that was editing. It's also important to detect that this thing happened. So now I have the more recent copy, the authoritative copy, because he had my copy that was in my past, and I was the only one that edited it. So if we can detect this, it's very simple to bring the again an illusion of a single copy to the system. I just pick my copy, I ship it to Marek, it's his new copy, and we are done. So this is one of the things also that we want to detect when things are ordered. And things will get more complicated when they actually are concurrent. So in the case that Peter was saying that the two of us did concurrent editings. So how can we do this in a more or less simple but inefficient way? So suppose that every replica has a globally unique name, say A, B, C, D. We arbitrate these names by some kind of protocol that ran before the system started. And then from appending to this name a counter, a growing counter, I can create my own different unique names. I can, if I am replica A, I can create A1, A2, A3, A4, A5, etc. and add to infinitum. This only grows logarithmically in terms of storage. So I can build a very simple theoretical device that is called a causal history. So when I have an empty document, everyone has an empty causal history, which in fact is a set. So it's an empty set that everyone has. Now it happened that I do my edit to the document. So I create a tag, a unique tag called A1, and I add it to the set. Okay. So now my copy of the document was changed and has a set with an element A1 on it, and all the other sets are empty. So we can compare these sets, and we can see that if we compare these by using the normal set inclusion operator, we see that my replica is dominating all the other replicas. So we are in the simple case that only one person edited, and we can ship my updates to all the other ones, and we get, again, a consistent state. So suppose that this happened. Now we are at a point where everyone has a set with an element A1 on it, and everyone has the same version of the document, okay, with the line that I added to the document. So now Peter is editing and is using the position here on Hangout. So I'm A, Christopher is B, Marek is D, and Peter is E. Yeah, sorry, Peter is D. So Peter will edit. It will create a tag D1, and we'll put it to the set. At the same time, Marek is editing, and it will create a tag C1 and put it on the set. Okay. So at this point, we have two kind of new versions of the document. Both me and Christopher are still late. Only have the tag A1. And we can see that if Marek tries to synchronize with me, he will have a newer version with respect to the version that I have. Okay, so he has a fresher version, and it's simple again. But if Marek tries to synchronize with Peter, we can observe that neither A1 C1 is greater than A1 D1, neither the other way around. So in fact, they did concurrent edits. So using this device that is called the causal history, we can kind of track what is happening in terms of a partial order, which is different from a total order. So in a total order, that's happened when only one of us edits at a given time. We can put all the documents in a single timeline, and we can know and follow the progress of this single copy of the document. There is no concurrency. But in this case, we have concurrency, and in case of concurrency, we have partial orders. So we could use this kind of device to track what's happening in the documents, but there's a big problem. It grows a lot. So it grows linearly with a number of updates that are done. So luckily, some people later on found ways to very efficiently compress this. And I think that Marek probably can lead into that and explain how this can be compressed.
Sure. So the idea is actually pretty old. I think it's probably older than me, actually. So the optimization is called version vectors. So in the word that Carlos was describing, we had this with each replica, we had an associated set of tags representing each update in the system, and when we wanted to know whether one replica is more up to date than the other, or whether it's like causally after another replica, we look at the set inclusion relation between these sets. We're looking whether all tags are included in the replica. And so idea here with version vectors is to represent the metadata differently. Here with each replica, we will store a vector of integers where each actor in the system, each process in the system will have an entry in this vector. And this will represent how many updates from this actor have we heard about so far. So if I have a vector with value 1 for Carlos and value 2 for Chris, I know that my replica contains 2 updates from Chris and 1 update from Carlos. And so each time I perform some update on a replica, I will update my entry in the vector. And when I send my updates to all replicas, I will include this vector, and the receiving replica will take a entry-wise maximum, will compute an entry-wise maximum of the incoming vector with its own vector. So let's say that Peter has so far heard just about the first update from Carlos and his own updates. So he has a entry 1 for Carlos and entry 1 for himself, and then he receives an update from me, where I heard from about 1 update from Carlos and let's say 2 updates from Carlos and 1 update from myself. So Peter will compute a maximum for entry for Carlos because now he knows about 2 updates from Carlos through me. So his output vector will be like 2 entries for Carlos, 1 entry for me, and 1 entry for himself. So once we maintain this kind of vector, we can actually tell what is the relation of replica with respect to the causality relation. If we see that, if you look at replicas and their vectors, and if we see that in my vector, if all entries dominate or are greater or equal than every entry in the incoming vector or incoming timestamp, I can and at least 1 entry is strictly bigger in my vector. And I know that my replica is more up to date, and I can safely overwrite with my changes something else. So that's the idea basically. Instead of representing a huge set of updates or causal history, we just summarize this efficiently with vectors, and we say, okay, there's a number per each participant in the system that tells how many updates from each of us we heard about.
So to go back to the example of our concurrent document editor, if we use the vector clock approach that Marek just described, each event in the system is essentially a update to the document. So it can be either I insert a line, or I hit save on the file, or something the application decides is a write. So what we've accomplished with vector clocks is the ability to say that 2 updates happen concurrently. This is what we wanted. So if I'm on a flight and Marek is in Paris, then when we finally synchronize, we can use our vector clocks to detect the concurrency. What we've essentially done is we've taken this causal history that is linear in the number of events that occurred in the system and compressed it down to a vector that is size of the number of actors that are actually performing updates in the system. And this actually works pretty well. So what happens is if I get a vector clock from Marek, an update from Marek that's tagged with a vector clock that dominates my current vector clock, that is all the entries are greater, I know that Marek has essentially just made a bunch of updates, and none of my updates are in conflict, or none of the updates that I've seen are in conflict. I can essentially just take Marek's update and completely overwrite my version of the file. If I've made updates to my file that are concurrent to, say, updates that Marek has performed or updates that Marek has observed from Carlos and subsequently has performed modifications for, I'm going to either have to perform a merge of my concurrent updates. So this might be, say, using some sort of text-based function that takes, say, my lines and Marek's lines does a merge, just like, say, Git does a merge when we have conflicts in our source trees. Or alternatively, might have to wait for, say, Carlos's updates, then Marek's updates, depending on how we represent the actual data. One of these results that's actually sort of interesting is that Carlos can maybe talk a little bit more about is the fact that if you want to represent a causal history where you have n actors, so here there's 4 of us, we can't represent this history exactly using smaller than essentially O of 4 or O of n amount of data. So basically, we can't compress causal history smaller than the number of actors that are performing updates in the system. And effectively, the idea is if I perform an update, I need some way to track. Well, the proof is actually using like algebraic homomorphisms, or like basically algebraic theory. But the idea is if I need to perform an update, I need some way to assign a new timestamp, and everyone might need to assign a new timestamp concurrently. Carlos, do you want to talk a little bit more about the result?
Yeah. So we basically need the same number of factors or the same number of entries in the vector as the number of concurrent actors that we have in the system. Otherwise, if we start using fewer entries, we get into another mechanism that is called plausible clocks that uses fewer entries. And if we go further down, we get a Lamport clock, which was introduced in the original paper that talked about causality, and basically it's a single scalar that represents everything. So maybe I'll just talk a little bit of what's the purpose of that, and for that we need to maybe relate a bit what is the relation of causality with real time. So there is a relation that more formally is called a consistency relation between the two. And this means that if I'm influenced by a given event, it must be that this event occurred in the past in real time. Okay, but there might be an event in the past in real time, and I might be concurrent with him. Okay, so real time introduces a total order, and causality is a partial order. So in a sense, these total orders lose information that was present in the partial order. Because they compress everything into a single timeline. So a way to do this, as I just stated, is to refer to real time, to wall clock time, but this implies access to wall clocks, which can be difficult in distributed systems. There are some trade-offs for using that, although there are some recent advances now on that. So Lamport also introduced the notion of a scalar clock, that is basically you do the same thing. You can you have a single scalar, and you do the following. Each time you do an update, you increase. So suppose that the current value I have is 10. When I do an update, I increase it to 11. Next update I do increase it to 12. So when I send to Marek, if Marek is still at say 10 and I'm sending 12, he didn't do anything, so he knows that my copy is more recent. But the problem is that if Marek is doing something concurrently, he is also updating the same counter, so it can already be at 12, and he will think that he has the same state that I have. Okay. So this kind of loses information, but it can be used by doing another trick to construct a total order on the system. When we are tied, so when Marek is 12 and I am 12, we can look at our replica IDs, say Carlos and Marek, and since C is less than M, I will win. So we can construct a total order using this device. And this total order is different from the real-time order, but it is again consistent with causality, and that's the nice property that it has, and it has been used on some systems that want to reconstruct this total order without necessarily doing consensus.
So just to be clear, right, the Lamport clocks, or using essentially a scalar clock, allows us to say something either happened before another, or one event happened before another event, or one event happened concurrently with another event, but we aren't able to tell whether or not it was concurrent or happened before, right? So if Marek performs updates 1 to 5, which are causally unrelated to my updates 1 to 10, when Marek and I compare timestamps, I have 10, Marek has 5, we can detect that either my updates were concurrent with Marek's, which is what actually happened, or we have to accept the possibility that my updates actually dominated Marek's. So the fact that this is useful for characterizing causality, but it's essentially lossy, right? So we've traded this O of n for O of 1, a very small timestamp. And in our concurrent editing application, what will happen is that we can't detect whether or not my update timestamp 10 should actually just overwrite Marek's, or if somehow there was actually a conflict, there were concurrent updates, and say we should invoke, say, text merge on the document. So we're essentially trading off precision for space efficiency.
And I think this can also lead us into a very common strategy that you know, that is last writer wins, where we also do this kind of trade-off, and several systems do this kind of trade-off. So in this case, if your clocks are working decently, you know that. So I normally try to say that last writer wins is great if there is a single user to the system, but using different devices. So if it's only me using either my desktop computer, my portable computer, or my smartphone, this is normally what I want. The last edit that I have done is the one that I want to prevail. Okay, but once we have multiple users acting independently, by doing last writer wins, we are losing updates when we have concurrent edits.
So just to come back, I think, to our original example, so the reason why we have a entry per actor in the version vector is that we want to update each entry independently. We want to be able to perform update on a replica, on my replica in Paris, without synchronizing with you guys in the States and with Carlos in Portugal. And to avoid high latency, I want to make this update independently. If you want to share a single integer, then we either need to synchronize on each time we generate a new integer, or we end up with something like Lamport clock, where we lose precision because we share a single entry. So that is like the intuitive reason why version vectors really need n entries, where n is a number of actors in the system.
So the cool trick that systems like Dynamo and replicated data stores do is they say, okay, we have this O of n. We want essentially everyone, well, in many systems, we want anyone who can access a replica to be able to perform an operation. But just because Marek and I say want to perform operations, if we operate in a system in a system model where our operations are performed on, say, servers. So let's say Marek and I and 1,000 other people are updating a document, but each of our updates goes through one of 3 replicas in, say, Google's data center. Well, instead of having O of 1,000, or basically 1,000 entries in the vector clocks, we can instead rely on the servers themselves to assign the vector clock timestamps. Now, what this allows is now we suddenly, instead of having ordered number of clients, we have order of number of servers entries in our vector clocks. If we want to just say capture causality for a single update, or for a single data item, let's just say we only want to capture causality for my Word document as opposed to the document I'm sharing with my girlfriend, then we can essentially bound it to the number of replicas for a given item. So in practice, this is really like 3 replicas or 5 replicas. That's 5 entries in the vector clock as opposed to thousands. And so if you see vector clocks in the wild, often they actually perform this operation, which says you can only perform updates if you are connected to a replica, but you only have to use order of replicas as opposed to order of updaters, which is fairly which both is sufficient to capture concurrent updates. We don't have this kind of this sort of ambiguity between concurrent updates and updates that happened before, but we also don't have the same metadata explosion. So we're essentially trading availability for scalability.
Okay, I think this is also building a kind of context to talk a little bit about a new concept, which is dotted version vectors. So when we are operating on that kind of setup that Peter just described, so we have say if we have 5 server replicas, we have 5 entries. That's okay, but we might have thousands of clients. So what can happen if you operate in a system similar like to Dynamo and React? which is a key-value store, it happens more or less like this. When a user reads a data item, it does a get operation, and it gets a context with the data that is reading, a metadata context that is showing the causality. So this context will have the current value of the version vector when the read operation occurred inside the cluster. And then the user will change the value potentially, and will submit it back with a put operation, and he will submit back the context. So if we only have one user interacting with the system at a single time, all goes well, okay? Because the context I'm supplying back is the same context that is still on the system, so it will be the new official context on the cluster. The problem is if we have multiple users doing this thing, okay? A simple way to avoid this, but not desirable, will be to only allow the first user to install his new value, and all the other ones we can detect that they have been operating over a past value, and we could reject their updates. But normally we are looking at systems that want high availability, so rejecting updates is not a good choice. So since we can detect this, what some systems do, like React, they create siblings. They detect this, and they detect that there were concurrent edits, that they cannot easily decide which things can be overwritten and are dominated, so they simply create siblings. They create multiple entries, one for each update, and they supply everything back for the next get operation. And the problem is that siblings can start growing and growing, and they will only be reduced once there is a good interaction where a given user read everything, no one else did anything concurrently, and he submitted back the context that is covering everything. And these updates can then substitute everything and reduce the concurrent siblings, the concurrent versions of the state to a single state. And what is possible with some work we did called the dotted version vectors is kind of represented in a more efficient way, so that when a user reads a given number of siblings, say the 10 siblings that were in the system at a given time, he can supply back a causal context that will enable him to reduce all these siblings to the new value that he's submitting, but still be concurrent with other changes that were done concurrently with his operation. It's a bit complex, but this is kind of the core idea. So it will allow reducing the number of siblings. The structure of the mechanism is kind of a version vector plus a single item of a causal history that can be separated from what is represented in the version vector. So in a system with 3 replicas, if you have a version vector with values like 10 to 1, you can then add it a single item saying like 12. So it says that the first replica did an update number 12 that is it does not follow 10 immediately, but it's a bit separated.
So okay, so we've basically gone through stamps or vector clocks, I guess, then stamps, and now bounded version vectors. One question that we thought would be worth discussing is, when is causality actually when is it sufficient for use in, say, a distributed data store or a distributed document service, right? So essentially, what we're doing by allowing clients to perform updates at any replica in the system is we're essentially enabling available operation. That is to say, every client that can access a copy of the data is able to make progress. And what this allows us to do is to provide each agent in the system with the ability to make progress. What this doesn't allow us to do is to require that what doesn't allow us to do is essentially control concurrency, right? So we're trading off availability of operation for the ability to make strong statements about the consistency of the replicated state. So, this is basically fundamental here. If you look at, say, the actual proof of the CAP theorem, for instance, what it talks about is the ability to make concurrent operations without having to synchronize. And there's actually a whole body of work talking about both protocols and semantic barriers for what's known as often lazy replication or optimistic replication, or increasingly what we just call a wide variety of eventually consistent systems. So essentially, we can't perform arbitrary updates in a highly available manner and maintain a consistent copy of global state. But what causality allows us to do is it allows us to reason about concurrent updates, essentially detecting them. And once we've detected the updates, we can often, not always, but often, repair the database and put it back in a consistent state. So one really interesting body of work that essentially looks at what happens when our replicas are essentially operating optimistically. Updates are being shipped asynchronously and opportunistically whenever they can, as is the case in many eventually consistent stores today, is work that I guess Carlos and Marek have done, along with some other smart folks, on what are known as CRDTs. So Marek, do you want to talk a little about CRDTs and how they basically take this notion of causality and allow consistent update despite concurrency?
Yes, of course. So the starting point for this is really what do we do when we detected the causality? Why actually bother with detecting causality? So when we know that things are causally related, we know that we can just when I know that my incoming value from another replica is causally related with my value, I know that I can just overwrite my replica of the new value. But when I know it's concurrent, I need this kind of merge function that will merge the incoming updates with my existing updates that I knew about at the time of receiving them. So usually, if you think of it in terms of interfaces like key value stores, where we store some opaque values, it's pretty hard to tell how to merge two opaque values to something meaningful. So one approach to that is to change a little bit the level of abstraction of reasoning, and instead of looking at opaque values, is to think of your database as a set of data types or set of objects of some particular data type. And CRDTs, conflict-free replicated data types, is a particular class of objects that you can use in these cases. These are objects which provide a merge function for concurrent updates, for concurrently updated replicas. So when I receive, so I can have, for instance, a set object such that when I receive some updates, I receive a replica state from Peter, I can merge, my set object can merge this incoming state with my existing state and produce something meaningful. So for instance, when we have concurrent operations on different elements, I can just easily apply them in any order, and I can easily merge these values. Whereas where we update the same element in a set, let's say that I add some member to this hangout, and Peter removes the same participant from the hangout concurrently, we can use our admin set, a special predefined set, and which will take care of this merge, and it will, in case of concurrent operation on the same participant, it will say, okay, adding participant has a priority, it's a constructive operation, and we'll all agree that this participant is now in a set. So it's important for this kind of merge function that it satisfies some properties, right? And one thing is that we want this function to perform in the same way at every replica, so we want it to be deterministic. And we usually want some other properties as well, such as commutativity and associativity. So composers with more complex situations where we have concurrent conflict resolution at different replicas happening. So CRDTs is basically a class of data types that developers can use and can avoid writing their own custom merge logic, which is pretty complex. It's pretty complex to ensure that things will converge to the same value. And instead, we just pick one of existing data types. Like I pick a set data type to represent participants in a Hangout, or I pick a counter data type to represent the number of views of this podcast. And then these things can be updated from the application level, whereas the data type level takes care of merging concurrent updates. So that's the idea behind CRDTs.
I will try just to add a simple connection between what kind of merge the CRDT does and what kind of merge is done by a user that is using a version control system and that is presented to concurrent edits and is doing a merge. So with CRDTs, we are talking about a deterministic merge. It's kind of a syntactic reconciliation. And this ties to what is happening to the vector when we supply back the merged value. So suppose that I read two replicas with vectors like 2, 1 and 1, 2. So it means that they were concurrent. So if I do a merge with this kind of syntactic reconciliation that is deterministic, I can derive a state with the CRDT mechanism that I can register back under the version vector 2, 2. So I take the pointwise maximum of the 2, it could be more, version vectors that I receive with the state that I am merging. Because I'm not doing any specific action. So the action is only dependent on the data itself. On the contrary, when we delegate the merge to the user, so a user that is presented with the same situation, a given text that is represented by a version vector 2, 1, another text that is represented by version vector 1, 2, and supposing that the user is the one associated to the first entry, so it's the first user, and is doing a reconciliation, so he's looking at the two documents, deciding which is the best title in the document, and writing that back, he should register this decision back as 3, 2, no longer as 2, 2, because he's taking a decision. It can happen that concurrently the other user is doing the same reconciliation and taking a different outcome on this decision. And we want to detect this again as a case of concurrency. Okay, so there is a relation between how we register things with the causality tracking, with the version vectors, and the kind of reconciliation that we are doing.
I mean, I think one of the really important distinctions that CRDTs make, and you guys touched on this, is that we have had systems that detect causality and will provide user-specified merge functions for since 1990s, right? So there's a project called Bayou that you may have heard of, which in the early 90s basically was from Xerox PARC, and they wanted to do mobile document management. Like you have a PDA and you want to be able to perform updates, and then you want to essentially reconcile those updates. Really forward-looking stuff for like 1994. And they had this idea, well, we'll just let the user essentially merge their updates. And actually, the Dynamo systems, Dynamo introduced in 2007, lots of systems like REAC and Voldemort that adopt the Dynamo-style vector clocks today essentially present this user-specified merge function, where essentially you have to merge your own concurrent updates. And the nice thing about CRDTs is you've got a bunch of expert PhDs and professors and grad students like Carlos and Marek that have essentially made sure that your merge is safe for a large class of useful data types, essentially allow you to get semantic richness of data types like Redis without having to actually perform a lot of synchronization on the fast path. One thing that I think is worth mentioning though is that not everything is mergeable. Like there are certain classes of updates that essentially you can't logically reconcile. So for instance, I'm going to appeal the terrible example of a bank account, but if we want to enforce an integrity constraint, that is to say our bank account remains positive, we have $100 in the bank, Marek removes $60 on his side, and I remove $60 on my side, then we've in total withdrawn $120. But now, when we merge, if we were to do simple, say, decrement of these counters, we would both end up with negative 120 in the bank. Okay, so I know, what do we do in this case? Well, first of all, this is basically saying our operations, that is to say, our bank account decrements, are not safe under concurrent operation. Now we can get Marek and I to agree. We can by basically saying, well, we'll just have one of our updates win. So if we were to say end up with 40, just say take my value, we could make sure our replicates actually agree. Like both replicates will contain the value 40, but this essentially violates our semantic principle. Somehow Marek and I withdrew $120. This is no longer reflected in the database. You can also do things, which is what many banks do in practice, actually, which is to say we'll compensate for concurrent operation that shouldn't have happened, essentially using some out-of-band process like chargeback like overdraft fees from Marek and I, but now we're starting to get outside of the scope of the system, and we're having to have external processes that compensate for this. But the high-level message is you better be able to somehow safely resolve concurrent updates, and if you can't, the optimistic strategies that many systems employ will be insufficient for the applications. It turns out that a lot of applications, this is actually fine, but you do have to be careful. And in the case that you essentially want to disallow logical concurrency, you need a total ordering, more or less, on updates, at least with respect to concurrent updates, whereby there is no concurrency for operations that should not be performed simultaneously or cannot be safely performed simultaneously.
Yeah. So one consequence of these properties that the merge function requires is that some metadata accumulates over time. Right? So if you think like how can you implement what can we give an example? Let's say we want to implement a counter. Let's say we do it first naive way. So one naive way of implementing a counter is just to each increment we add a unique tag to some sets. And so each time I increment, I create a new tag, and during merge, I just take a set union of tags. If I assume that every tag that I create in the system is unique, the number of tags in my current metadata represents the value of a counter. Right? So this makes sure, for instance, that where I receive counts from Carlos, and then I receive indirectly the same counts from Peter, my set union operator on these tags will be able to distinguish that, oh, these are the same tags that I previously received, so I will not count the Carlos counts twice, because I will be able to distinguish them by unique identity. But the downside of this is that over time, we're gonna have a counter that has metadata that grows linearly with the number of updates. So again, like similar problem as we described at the beginning with causal histories, and we do some effort. Basically, we did some works recently on and other people do some work basically on how to avoid these costs of growth of metadata. So some stuff are doable, some are not. So one thing that we can do is with a counter, we don't need to use this unique tags to implement counter. We can use something similar to version vectors to implement counter, where we just keep information about how many updates each actor has performed, how many increments, and then when I adapt these entries in the vector, I have my value of a counter. There are some more difficult cases. There are cases with sets where sometimes we require that sometimes we need to keep information about removed elements from the set, like to implement adwin strategy. We have some design that prevents storing this information where we summarize by version vectors. But there are some data types where these things are harder, like collaborative editing documents, like list data type, where you want to store an ordered list of elements. And this one, for instance, there is no known strategy to discard garbage. So that's like a quick story. Maybe Carlos, or you guys have something to add while I bring up the lights.
Okay. Maybe I'll talk a little bit about an issue that we referred in the beginning. Is that for all of these things to work, we need each actor to have either a unique name or a unique position in a vector, which is basically the same thing but a little more static. So how do we get this thing? So basically, if we want to do it with the system running, we need consensus to arbitrate these unique names, or we do it in a kind of prior consensus. We do it before starting the system. When the administrator is configuring the system, he is going to tell the replicas what are their unique names. Or we should use some probabilistic approach that might have problems if we are unlucky.
It depends if you're religious and believe in UUIDs or not, right?
Yeah, I believe in Murphy, so
I mean, so if you're playing along at home, right, it's probably okay to use get UUID, and the chance of collision is remarkably low. But say for provable non-collision, you would need some sort of agreement protocol.
Yeah, and to recap, what happens when we are sharing the same ID is that we got into the problems that we have with plausible clocks and Lamport scalar clocks. But suppose that we have these unique IDs. An interesting thing that I don't know if it's well known is that you can have multiple IDs if you want, and you can even update on all the IDs that you have control of, and it works okay. Okay, so it brings no problem. Everything works okay if you use any of the IDs that you have available. So it's possible to build a system where you get several IDs, and when a new replica wants to be created, it can contact another replica and ask it, okay, do you have an ID? You can give it to me. And if we have a safe protocol to hand off this ID from one replica to the other, which might be very tricky if we don't have a synchronous connection, then you can hand over the ID to the other replica, and you keep the sanity in the pool of IDs. But we have this problem is a very important problem. If you think at very long-lived systems where you have servers that have been active in the system like half a year ago, they are no longer active, but their IDs are still polluting all the replicas. So it's probably a good thing to have a way of having a kind of controlled shutdown of the server so that you can take hold of that ID and reuse it later. Okay, maybe should just refer a little bit about very high level this relation between vector clocks and version vectors. So we have decided kind of talking about the case where we are handling replicas of data. So the events we are interested in are and those that get into the causal history is the update events, the event that you do when you change the data replica. But causality and in its origins, and it has a very wide use for many other things under the form of a mechanism called vector clocks, where you order more things. You order internal process events that occur when you do a computation at a given process. You order message send events, and you also want to causally relate the message receive events. And this can be used to do lots of important algorithms in distributed systems. The representation is the same as version vectors. There's only a slight difference on the update rules that are used.
So I think among those representations that of different techniques of tracking causality that we mentioned, there's probably one thing that we did not speak about so far, unless I missed something, which are hash histories. So this is like a quite different strategy of approaching the problem. Instead of using any kind of vectors, each time we maintain a set of hash of updates. Each replica maintains a set of hash of updates that it's previously performed, that it includes. And whenever we generate a new update, we refer to the hashes of updates that we have knew previously, and basically this allows us to construct a graph of these hashes of values and relate events using this graph directly without involving any vectors. But the bottom line is that we need to maintain a graph which have a pointers from one hash to another, and again this has some costs. So the cost is usually with the number of updates. So this is like a little bit similar to the causal histories in the worst case. But there are some use cases where this may be useful. So this is definitely useful when we have systems that keep history of all old versions, like version control systems. There is like nearly no cost of storing. There is no cost of storing a hash of the value that was previously in the system, or systems where we have lots of different actors, but we have not so many updates actually. So we have mostly reads. In these cases, this technique may be more efficient than vector clocks or version vectors actually.
I'd just like to add another very simple aspect to have a more complete coverage. So when we were talking about this editing to the document, we were saying that for each time we change something in the document, we are increasing our number in our position in the vector. In fact, if we are editing and we don't communicate with anyone what we are doing, we don't need to keep increasing the position. We just need to increase it once, and then we can keep editing the document. And then after we ship the changed document, then if we want to edit again, we need to increase it again. So this thing is called update coalescing, and it's tied to the fact that the size of the edit is not specified. So you could change everything in a single edit, or do many edits in isolation that change small things. So there is no need to increase every time if you don't communicate.
So this is basically saying, how do we adjust the actual granularity of a given event, or what do we call an event in the system?
Yeah.
Is that correct?
Yeah.
And one of the things actually that that we've looked at a little bit as an alternative approach to the O of n blowup is to say, well, can you even disregard certain events in the causal history based on application level semantics? So we call this explicit causality, where we basically say, well, instead of dealing with the O of n problem, if I'm on Twitter, for instance, and I read 600 updates, but reply to Chris, I don't really care about most of those causal orderings, right? My tweet was maybe influenced by 200 of the tweets that I skimmed through, but just as likely I'm actually just replying to Chris's tweet, and that's essentially the most important part of the message that I care about. So an alternative to this kind of scalability challenge that we've advocated recently is to say, well, just defer to the application and let the application decide what they want to call an event or not. And moreover, only essentially combine these, only explicitly materialize event histories the application cares about. Just an alternative that's worth considering, and we've done some analysis for real-world workloads, and you end up getting a much, much smaller graph. Like for Twitter, you have a graph where you can just materialize one-hop dependencies, and on Twitter reply to, that's literally like one piece of metadata for each tweet, because you just use the in reply to that's already stored in the tweet already. For other things like, say, Facebook updates and privacy settings, you have maybe essentially two or three pieces of metadata along with every update. But again, what we're doing here is we're saying, well, let's redefine what a causal event is, and let's let the application tell us what causality actually matters for it. So
Anybody?
There's this really great survey you guys have written. I guess we can provide the link later, but it's called it's by Schwartz and Matter, called Detecting Causal Relationships in Distributed Computation, and it's got literally like the best subtitle ever, which is in search of the Holy Grail. And it actually steps through both the causality problem, right? So what does it mean to detect causal relationships? It talks a lot about different techniques for detecting causality, and it even gives a reasonable overview of that impossibility result we talked about later. So it's like a 40-page document. It's definitely covers a lot of techniques that I haven't seen in production, but even just skimming that should give a pretty reasonable understanding of essentially the state of the art as of, I don't know, early 2000 when it was written. It's literally my go-to reference for almost all of this stuff. It doesn't talk about applications of causality so much as detecting causality, but there's some other, I mean, you can go to, I don't know, does anyone have ideas for applications? There's a couple other papers you could recommend.
Yes, I think to pick it up from here, I guess a good reference to look for how to apply these techniques is the survey by Yas Saito and Mark Shapiro. It's optimistic replication from 2005. This gives like a good idea of how to use these different techniques, version vectors, hash histories, and so on, in the replication system that is optimistic replication system or eventually constant system. That's also available publicly.
I think those two surveys are like probably the best that I've seen in this whole area of weak consistency, weak isolation, high availability, and that the people who wrote them are well versed in the field, but also seem to have done a reasonable job distilling the stuff, which is rare at times.
Okay, so people can look for that on. So the first one is on. It appeared on Springer Distributed Computing, and the Matten survey. I think it's Fitch and no, sorry, confusing with another thing. But it's there on distributed computing, and the survey on optimistic replication is on ACM computing surveys, and probably they can be found around in the internet. There are probably other versions.
Any final comments? Any final thoughts?
Well, I think we try to cover several bits of a somewhat complex subject. I hope that the listeners got a general idea. We are only grasping the surface, specifically by not covering the details around vector clocks. But I think that you can all get an idea of how these things interact with specifically with key value stores in this context.
I think, given that Marek is out, I'll weigh in. I think one of the reasons why causality in general is so important in distributed systems is the fact that humans experience causality in the everyday world, right? So when I, drink my water, I assume that my water was placed on the table because of some prior action that I took. There are things, yep, exactly. So there are, we expect certain things to be a certain way. We expect that if I see a guy get shot, I shouldn't see the gunshot after I see him getting shot, or something less morbid than that. And so, to the extent that it's possible, causality in distributed computations allows us to reason about partial states in a way that is at least cognitively congruent with the way that we interact with the world, right? So I live my life as if my apartment is not currently on fire. I don't know that my apartment is on fire. If it is on fire, it's likely, from the perspective at least my everyday interactions, concurrent with the fact that I'm on this podcast right now. And I somehow, as a human, am able to reason about these inconsistencies between my worldview and the state of the actual world. Now, I can't prevent concurrent things from happening, but somehow knowing that events occur typically in causal ordering, certainly in the physical world, often not in the information world. So I might hear about an event on Twitter before I see it, maybe in the news. But real time-based causality, as Carlos mentioned. So basically, we're mapping a pretty natural model onto our distributed computation. It's not perfect, but it's a lot easier than completely asynchronous, completely unordered computation.
I'd just like to add just a single aspect to what Peter said is about the concept called external causality. So the causality that these systems are modeling is what the system thinks that their users are seeing, but there might be external channels. So in this initial example, when we are having concurrent edits, it might happen that Marek gave a phone call to Peter and told him, okay, I just did this thing, and the system will never know about that. Okay. So system designers must beware also of this possibility, but there's no way to capture this if the system has no information on it.
The notion of scope in causally consistent systems is actually was actually the subject of a really famous debate in the 1990s. You may have heard of it. It's called the paper title is called "Understanding the Limits of Totally Ordered." Totally and causally ordered, basically totally and causally ordered communication systems, or basically it's abbreviated CATOX, and it's by David Sheraton and Dale Skeen, and there was a big back and forth between these two guys. One of them was at Stanford, and this guy Ken Berman, who's at Cornell, who did stuff like ISIS, which you may have heard about, basically discussing the pros and cons of causally ordered communication systems. One of the major complaints was one of the ones that Carlos brought up, which is just say, you can't always capture all of your causal dependencies if you're limited to a scope of a single system like a communication system, where just because I am on Google Hangout with you guys doesn't mean I'm not also on the telephone with you. So it's essentially a scope dilemma. Kind of fun reading. Certainly people were caring about this in the 90s as well as today.
Yeah, so to add something to what Peter said, about the importance of this stuff, importance of causality, and that's sort of related to the scope question. Actually, it's also important at the level of the programmer that actually deals with the system. So when I program a system and let's say it ensures me some form of causality, then I know that when I'm rendering a page with the album of photos, I know that when I access a photo, definitely the album that was created causally before also exists, and that may simplify my role as a programmer. And similarly, at the level of stuff like CRDTs, the knowledge about the causality between events, allows to perform more meaningful actions, basically, or program systems easier. So it's probably appears important at both user level perspective and the programmer level perspective.
Okay. Sweet. Well, thanks for joining us, everybody. It's been awesome. We'll definitely get a link to all the papers that were mentioned up in the show notes, and get a link to the video and the audio version. So thank you very much.
Thanks for having us.
It was great.
Causality for the win.
Excellent. Thank you.